Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Introduction to Photovoltaic and Solar Radiation from the paper Energy Related Materials. So students, the main points which will be covered in this module are: first, the history of photovoltaics and the meaning of photovoltaic effect. Second, detailed note about the solar radiation and the black body radiation. Third, solar constant and photon flux and their calculations will be discussed. Fourth, the photosphere and the solar radiation. Lastly, we will discuss the effect of apparent motion of the sun on the solar cells. Let us start with a brief introduction about the module. Present energy ingestion mainly depends on fossil fuels, which are limited in the nature, and their overconsumption can cause environmental issues such as global warming and greenhouse gas emission. This has encouraged various researchers to search for an alternate, clean, and environmental friendly energy resources. Solar cells, they are one of the most promising, clean, and readily available energy resources that works on the basis of photovoltaic effect. In photovoltaic effect, there is the absorption of the incident light on the semiconductor material, generating the electron-hole pairs, which are further get separated, that is, electron to the negative terminal and hole to the positive terminal, by device structure, and generates a significant amount of electrical energy. So the device that converts the photovoltaic or the solar energy directly into the electricity is called as the photovoltaic cell or a solar cell. Let us discuss or recall the history about the solar cells. In 1839, there was a French physicist, which was Alexander Edmond Becquerel, who observed that there was a light-dependent voltage between the two electrodes immersed in an electrolyte. Then, in 1876, the same effect was demonstrated in selenium. Later, in 1883, the first solar cell was built by Charles Fritz, who coated the semiconductor selenium with an extremely thin layer of gold to form the junctions. The device was only around 1% efficient. Next, later on in 1941, first silicon-based solar cell was demonstrated. In 1946, there was a scientist, that is Russell Ohl, patented the modern solar cell, and it was a US patent. In 1954, there was a beginning of modern solar cell research. Finally, in 1958, first spacecraft is using the solar panels, and it was by US satellite Vanguard 1. Photovoltaic effect. This effect is the basis of the conversion of the sunlight directly into the electricity. When light is absorbed by the matter, photons are given up to excite the electrons to higher energy states within the material. And the condition for this is that the energy of the photons, that is h nu, must be greater than or equal to Eg. Students, we can say this condition in the other words as that this occurs when the energy of the photons making up the light is larger than the forbidden band gap of the semiconductor. The excited electrons relax back quickly to their original or ground state. So in a photovoltaic device, there is a built-in asymmetry due to doping which pulls the excited electrons away before they can relax and feeds them to an external circuit. The extra energy of the excited electrons generates a potential difference or electromotive force EMF. This force drives the electrons through a load in the external circuit to do an electrical work. Now let us discuss what is a solar cell. Solar cell is also known as a photovoltaic cell or PV cell. This is basically a device that converts a light energy, that is a solar energy, directly to electricity. It supplies a voltage and a current to a resistive load, that is the light, battery or motor. And the power is nothing but the current multiplied by voltage or the current square multiplied by R or voltage square by R. The term solar cell is designated to capture the energy from sunlight, whereas PV cell is referred to an unspecified light source. It is like a battery because it supplies DC power, but it is not like it because the voltage supplied by the cell changes with the change in the resistance of the load. So as you can see that there are 3 solar cells have been shown, where the first one, all the sunlight is falling on the solar cell. In the second one, half of the sunlight is falling on it. And in the third one, it is totally dark. Now let us discuss how does this photovoltaic or the solar cell works. The figure shows the schematic of a general photovoltaic device. The photovoltaic field is getting major attention as an alternative energy resource due to the fuel crisis and increasing energy demands. This technology offers simplicity, cleanliness, and direct conversion of solar energy into the electricity. So as it is evident from the figure that there are 2 metallic conducting strips, and this is covered by a glass lens which is used to focus the solar radiation from the sun onto the metallic conducting strips. Now these Electrons and the holes, they are separated by the external potential which has been applied on these metallic electrodes. As you can see that there is a N-type silicon bar and a P-type region in order to form a PN junction diode, and this yellow part shows the depletion region. So when the light falls on the diode, the electron-hole pairs are generated and they are separated due to the external potential applied. A symbol of a PV cell is also shown. So there are various advantages of solar cells over other conventional power systems, such as: first, solar cells produces electricity through direct conversion of solar radiation into electricity without involving any thermal process. Second, solar cells are quiet, reliable, modular, durable, and compatible with almost all environments. Fourth, solar cells can be utilized and located at any place. And fifth, solar cells, they have high power to weight ratio in comparison to other energy resources. However, solar cells, they have some disadvantages, such as solar cells show poor conversion efficiency, the fabrication cost of them is very high, and lastly, the solar energy is irregular, as solar cells generates electricity only when the sun shines, which varies with effect of solar intensity. However, solar cells have been utilized in various promising applications. The use of solar cells in space program is one of the most important applications for the last 25 years and is still one of the important application. There are more than 500 satellites in various orbits in the space which are being powered to a large scale by solar cells. However, the use of solar cells to provide electrical energy for terrestrial applications will be certain if the problem of economic availability of them has been solved. Hence, in order to provide reliable and competitive electrical power for terrestrial applications, solar energy field brought to an intensive research platform around the globe during the past 2 decades and are expected to continue to do so. There are various types of semiconductor materials which are being used for solar cell fabrication to convert the solar radiation into the electrical energy. These materials include silicon, gallium arsenide, cadmium sulfide, cadmium telluride, etc. Amongst them, only silicon and cadmium sulfide has given promising results. The solar cell based on single crystal silicon provided an efficiency of about 20% at air mass 1 isolation. However, the high cost limited its use in terrestrial applications. Hence, in order to reduce their cost and make them economically feasible, solar cells need further investigation. The high cost of silicon solar cells is not only because of high fabrication cost, but it also includes assembling many cells into a large area and make them durable and weatherproof. On the other hand, The thin film solar cells based on cadmium sulfide are less expensive than silicon solar cells. However, these cells are operated at a much lower efficiency. Now let us discuss what is a solar energy or what are the sources of solar radiation. The sunlight from the sun is the basis of life on Earth. It determines the surface temperature of the Earth as well as provides energy for all kind of natural processes on the Earth. Furthermore, the application of photovoltaics or solar cells depends on the availability of sunlight. So, the sun represents a sphere of gas heated by nuclear fusion reaction at its center where hydrogen atom melted into helium-1. All kinds of hot bodies released electromagnetic radiation with a spectral distribution which determines the temperature of the bodies. The sunlight from the sun is the basis of the life on the earth, and it originates with the thermonuclear fusion reaction. Also, the solar energy represents the entire electromagnetic radiation, that is visible light, infrared, ultraviolet, X-rays, and radio waves. The radiant energy from the sun has powered life on Earth for many millions of years. Now, as you can see from the figure, that the region where connective transport provides the way for the radiation is called as the photosphere. Solar irradiance. Solar irradiance or solar constant, that is ES, is defined as the amount of radiant power that perpendicularly falls from the Earth's atmosphere from the sun per unit area per unit time. Solar constant varies as a function of wavelength at a point outside the Earth's atmosphere, and it has its maximum value within the range of 0.3 to 0.8 micron. Generally, this radiation intensity, which describes the solar constant, is alternatively known as AM0 radiation, which is shown by the red curve in the graph. The AM0 radiation stands for air mass zero radiation, which means that sunlight has not passed through the Earth's atmosphere. This graph shows the value of the spectral irradiance or the solar constant as a function of wavelength for AM0 radiation, AM 1.5 radiation, and 6000 Kelvin black body. The figure shows the Sun-Earth system where the distance between both of them is approximately 150 million kilometers. The Sun emitted a solar radiation of 3.854 multiplied by 10 to the power 26 watts in all direction in the space out of which a small fraction is being received on the Earth. So let us assume a sphere around the Sun of radius r is equal to RSE as shown in the figure. The amount of solar radiation spreads over the entire area of sphere at this distance. Hence, the amount of power density or solar irradiance or solar constant outside the Earth's atmosphere can be written as ES is equal to radiation power divided by the area of sphere, which is equal to P sun divided by 4 pi RSE का square, which is equal to 3.845 multiplied by 10 to the power 26 divided by 4 pi multiplied by 1.496 into 10 to the power 11 the square. This is come out to be 1367 watt per meter square. At present, this value is accepted as the solar constant and is being used in the fabrication of photovoltaic cells. The photon flux is an important parameter used in solar cell calculations, which is defined as the number of photons passing through a unit area perpendicular to the light beam per second. If we consider the solar intensity phi in watt per meter square, then the photon flux can be described by phi is equal to n photon multiplied by E, which is equal to n photon multiplied by hc by lambda. So the n photon is equal to phi lambda by hc. Energy from the sun. About half the incoming solar energy which reaches the Earth's surface, the Earth receives 174 petawatts, that is 10 to the power 15 watts of incoming solar radiation at the upper atmosphere. Approximately 30% is reflected back to the space, while the rest is absorbed by the clouds, by the oceans and the land masses. Earth's land surface, oceans and atmosphere absorbs solar radiation, and this raises their temperature. The sunlight, which is absorbed by the oceans and land masses, keeps the surface at an average temperature of around 14 degrees Celsius. So, by photosynthesis, the green plants, they convert solar energy into the chemical energy which produces food, wood and the biomass from which the fossil fuels are derived. The amount of solar energy reaching the surface of the planet is so vast so that in 1 year it is about twice as much as will never be obtained from all of the Earth's non-renewable resources of coal, oil, natural gas and mined uranium combined together as intermittent sources. Solar and wind rays issues. Air mass. Usually, the intensity of the solar radiation is reduced by approximately 30% after passing through the Earth's atmosphere. The major factors which affects the intensity of solar radiations are Rayleigh scattering, that is, scattering of sunlight by the molecules present in the atmosphere, scattering of sunlight by dust particles and aerosols, absorption of solar radiation by the gases present in the atmosphere such as oxygen, ozone, water vapor and carbon dioxide, etc. The most important parameter which determines the total irradiance power under clear condition is the length of the light path traveled through the atmosphere, which is the shortest distance when sun is directly overhead. The ratio of any actual path length to its shortest distance is called as optical air mass. Hence, in this situation, that is, when sunlight is right overhead as shown in the figure, the optical air mass is unity, that is, optical air mass 1 or AM1 radiation. When sun is at some angle theta to the overhead, air mass can be written as air mass is equal to 1 by cos theta. Hence, optical air mass 2, that is AM2, in the figure will result when the sun is 60 degree off from the overhead. So the simplest way to calculate the air mass in practice is to measure the length of the shadow S cast by a vertical object of height h. We can write the air mass is equal to root of 1 plus S by h the square. The intensity of the solar radiation while reaching the Earth's atmosphere is attenuated at all the wavelengths. Hence, the solar radiation within the Earth's atmosphere varies significantly both in the intensity and in the composition. The AM 1.5 spectrum has been established as standard spectrum for measuring solar modules as it arrives in spring and autumn and can be viewed as an average year's spectrum. Global radiation or the direct and diffuse radiation. The composition of terrestrial sunlight or AM0 coming from space got weakened due to various effects such as scattering and absorption. Hence, in the summation of AM 1.5 spectrum, we received only 835 watt per meter square. Thus, out of the originally available solar radiation, that is 1367 watt per meter square, the Earth receives just the 61% of radiation, which is called as direct radiation. Furthermore, atmospheric scattering of light gives rise to significant results in indirect or diffuse radiation. So both the direct and diffuse radiations, they are schematically shown in the figure. Here the weak radiation portions coming from all directions of the atmosphere and are added to diffuse radiation. So the sum of both the direct and diffuse radiation is called as global radiation, that is represented by Eg is equal to E direct plus E diffuse. Generally, the contribution of diffuse radiation is often undervalued. However, in Germany, the diffuse radiation added a greater contribution to global radiation than direct radiation throughout the year. For example, in Hamburg, the average diffuse radiation or H diffuse is 1.52 kilowatt hour per m square d against a H direct of 1.08 kilowatt hour per m square d. Hence, the diffuse radiation contributes almost 60% to the yearly global radiation. On the other hand, in Munich, the position is somewhat changed, thus diffuse radiation here only contributes of around 54%. Diffuse sunlight has different spectral composition than direct sunlight, that is, it will be richer in shorter or blue wavelengths, which provides further availability in spectral composition of light received by a solar cell system. The solar cell device, based on concentrated sunlight, generally accepts the light rays crossing a limited range of angles. Hence, they usually have to track the solar radiation to utilize the direct component of sunlight with the diffuse component wasted. This tends to offset the advantage gained by such tracking systems of intercepting maximum power density by always being normal to the sun's arrays. The apparent motion of the sun caused due to the fact that the earth rotates about its axis, which is caused by the rotation of earth about its axis, changes the angle at which the direct components of light will fall on earth. So for a viewer which has a fixed location on the earth, the sun appears to move throughout the sky. The position of the sun depends on the location of the viewer on earth, the time of the day, and the time of the year. This apparent motion of the sun is shown in the figure, that is, for a viewer at altitude 35 degree north on any day, the plane of the sun's apparent orbit lies at an angle equal to the altitude from the viewer's verticals. At the equinoxes March 21st and September 23rd, the sun rises due east and sets due west. Hence, the altitude of the sun at solar noon during these days equals to 90 degree minus the latitude. At the summer and winter solstices, June 21 and December 22, the altitude at the solar noon has increased or decreased by the declination of the earth, that is 23 degree 27 minutes. So students, let us summarize what we have learned in this module. Outside the Earth's atmosphere, the sunlight is relatively constant. However, on the Earth's surface, the situation is more complicated. The intensity and the spectral composition of terrestrial sunlight varies dramatically and unpredictably. On a clear day, the optical air mass is an important parameter. The global radiation, that is direct and diffuse radiation, is important for less ideal conditions. Thank you.